Okay, hello everyone. Today will be a special video because I'll be trying to solve as many C's as I can, which covers from anthem tests or divergence tests up until I believe would be power series. I'm not sure whether or not I can like enter to Maclaurin series. Who knows? Maybe I'll give it a go. I'll try to solve a few. But Yeah, today we'll be focusing on convergence, absolute converge, no converge absolutely, converge conditionally, and diverge. So all the tests you'll try to apply, and we will start from the simplest ones to much more difficult ones. And let's see where we can go. So the questions are from Thomas Calculus, so that will be my reference for the questions for today. All right, so question 25. So we have a series, n is equal to 1 to infinity, 1 divided by square root of n. Now, this is a p series where we know that the square root implies n to the power of 1 over 2. Now, we know that p series, if p is less than or equal to 1, the series diverges. Alright, the series diverges. So, well, it diverges because the p is equal to 1 over 2, where 1 over 2 is less than or equal to 1. So the way I wrote the answer, I'm write the answer as um, diverges by the p series, where we know that the p value is equal to 1 over 2. Okay? Alright, 26. Now we have another series, and I believe everyone is familiar with this one, which is negative 5 over n, where we bring out the constant multiple outside of the series. And we know that the series is a harmonic series. So we say since this diverges because it is a harmonic series, because it's a harmonic series, then also diverges. Okay, we don't need to check whether when we put the absolute value it converges. Well, it converges as well. Diverges. It diverges everything, whether you put the absolute or not for this case. Okay, but the next case will be the alternating series, which is question 27. So now you want to see whether it diverges or converge conditionally. Okay, right. So we have n is equal to 1 to infinity, negative 1 power of n over square root of n. We know by putting the absolute value, let's say this is our an. So when we put the absolute value over down here, the negative on the numerator here, the negative 1 to power of n, we can get rid of it, and we can get rid of the absolute value as well. We are left with this. Now previously, we discussed that this diverges by the p series. So this diverges. But this diverges implies when we have the absolute value. It does not imply that this series diverges, not yet. But how do we determine whether the series without the absolute value diverges or converges? Now, the way to do so is by using one of the alternating test series. Now, what are the conditions for alternating test series? There are three. The first one will be, I'm going to make a bullet point. The first one will be, let's say we have, I'm going to make it general. We have a series And an alternating series, so we have u as subscript n. So the first one will be u subscript n has to be positive for all n, where for here we have n is equal or larger than equal to 1. Now the second point will be the previous term is larger or equal to, but is larger than equal to n plus 1, the next consecutive term. And the third one will be the limit as n approaches to infinity for the nth term here will be 0. Okay, so if all of these conditions are true, therefore it converges by the alternating test series. Okay, so let's go through the first one. So is it a positive term? Well, let's say let un is equal to 1 over square root of n. And as you can see, square root will always be positive no matter what. Well, because our domain n is a positive natural number, therefore we could say un is larger than 0 for all n larger or equal to 1. The next one will be we want to show that the previous term and the next consecutive term, where the previous term is larger than or equal to with the consecutive term, the next consecutive term. So the way we want to show is this. We will try and build an inequality, but from here, you don't need to put the inequality sign yet, unless you're certain that as you solve this algebraically is always larger than equal to this sign here. Now remember, you could apply the operations like multiplying both sides, dividing both sides, and the inequality sign will not change. It's because that our value will always be positive. So that's the good thing about it. So let's multiply both sides with the respective denominators, and we will have n plus 1 square root of n. Square both sides, you have n plus 1 and n, then you are left 1, 0. So as you can see here, our left hand side will always be larger or equal to the right hand side. It's true still. So from the beginning up until here, it is true for all n larger or equal to 1. Okay. So now last one will be the limit. Now this is trivial. For calc 1, we've learned calculus 1, and we can evaluate the limit. We know that the denominator will be larger. As it becomes larger, the whole term will be approaching 0, so that is true. Therefore, this series, alternating series, converges. Now, what does it imply? Then this series, since the absolute, when we place the absolute on our series, it diverges, but then without the absolute, it converges. Then, by definition, this is we converge conditionally. It converges conditionally. There you go. Okay. All right. So hopefully I'm correct. I think so. Yes, sir. Yes. All right. Nice. Okay. So let's go through with question 28. Now, question 28, we have another P series to n power 3. My apologies if there's a loud noise in the background because they're doing some cleaning. But hopefully my voice is a bit loud enough to give a proper explanation. But yeah, this is not a good timing. They are doing this, but hopefully we can go through together. So, oops, there's an on my screen. So we have a series, and it's a P series. But it's not a P series yet. The constant multiple we will be bringing up from our series here, so 1 over 2. Now this is our P series, and the P series, okay, we'll write down as is a P series, is a P series where P is equal to 3 larger than 1. Therefore, this P series converges. Converges implies that the multiple, well, it converges as well. Now, Whether or not it converges absolutely, well, obviously you put the absolute value sign and it still converges no matter what. So let's just show that this converges as well. Therefore, it converges absolutely. Very nice. Converges absolutely. All right. Let's go to question 29. Now, question 29, we have another alternating series. We have another one, about 1n over ln n plus 1. It's 11 a.m. I thought they were doing it like 8 or 9, but 11. Damn, bro. Even so, it's very hot outside, and they are doing it elegantly. Okay, so, alternating series. Okay, now alternating series. Okay, let us try and see. Okay, let us put the absolute value and see whether it converges or diverges. So by putting, oops, sometimes my sigma notation is not very pretty, but it works. Okay, by placing this absolute value, it will be n is equal to 1 infinity 1 over ln m plus 1. Okay, now converge or diverge, we could use direct comparison test, I believe, where we can compare with um I believe we can compare 1 over ln n, but then we can compare with e. Yeah, we can compare with e, no problem. No, sorry, 1 over n, sorry, we can compare with 1 over n. 1 over n, we can compare it with 1 over n. Okay, so DCT is short for direct comparison test. So direct comparison test, if we can find a diverged series and it's less than with the series that we have here, then the diverge lah. But if we can find a converging series, it has to be larger than our test series, which is this one. So you have to refer back to your diverge and converges. Okay. All right. So what are you going to do? Direct comparison test. Now we want to compare with this series. And this series diverges because it's a harmonic series. Harmonic series. Diverges, harmonic series. And now I would like to build the inequality firsthand. So let's build that first and then we can make our conclusion. Okay, 1 over n. So when we multiply both sides, we have n ln n plus 1. And when we raise e both sides, we will have e power of n. And then, well, e to the power of ln n plus 1, we can cancel out e and ln. We are left with n plus 1. Sorry, my apologies. Okay, that's the idea we're going to do. So yeah, so here we have n plus 1. And as you can see here, an exponential function with a linear function. Well, exponential functions will be larger, will always be larger, right? It will always be larger. So as n approaches to infinity, e to the power of n will be larger faster. Okay, now that's the concept we'll be using. Therefore, this inequality is built upon. Now, by that comparison test, since the series, both series are positive series, have positive terms, sorry. So we can build an inequality as so, 1 over n, 1 over ln n plus 1. So this is true for all n larger equal to 1. Okay, now direct comparison test says that if the diverging series, okay, the one which we are using is less than or equal to with the series that we would like to know whether it diverges or converges, then 1 over ln n plus 1, the series diverges by the direct comparison test. So here we go. And 1 infinity one diverges. Okay. Now remember, diverges implies for the absolute value. So how about the original series? Well, remember, alternating test series. So let u subscript n as 1 over ln n plus 1. Okay, this is for the absolute. Okay, I assume all of you know this is for the absolute, not the original series. Doesn't imply the original series be diverging. So here let un is equal to 1 over ln n plus 1. Now we know that this will always be positive for all n larger equal to 1. Alhamdulillah, sorry. So number 2, you want to show that this is larger than the next consecutive term. So as usual, you solve it algebraically. There are two ways. First, um, the first way is that you differentiate, and then you see that for all n, the function, all right, the function decreases. But to do so, you have to define a function. You can't just differentiate the n term. You can't do that. You have to define a function that you see they both have the same behavior. Then since the function decreases as n approaches to infinity, implies the sequence also decreases as n approaches to infinity. Okay, but here this is an easier one for me. So here you multiply ln both sides, you will have ln n plus 2, ln n plus 1, raise e, you will have n plus 2, n plus 1, 2, 1. It's true for all n. Okay, for all n larger equal to 1. It's true. Now the final one, well, the limit, and we all know the limit approaching 0, because as n approaches to infinity, the denominator approaches to infinity, the whole term approaching to 0. Therefore, by the alternating test series, this converges. By the alternating test series. ATS stands for alternating test series. It's a simpler way for me to write it down. And then again, it's not a conclusion, it's a implication. And therefore this implies that this series converges conditionally. Conditionally. Right? Okay. So far so good. And what else that I can do here? So right. Yeah, I think that's the correct answer. Which is this? This is question 29. Alright. Question 29. Yeah. Okay. So let's go with question 30. Now, question 30, we have this following series n to infinity 1 over n ln n square. Okay. So 1 over n ln n square. You could do integral tests, but you have to fulfill the three conditions. The function has to be positive, decreasing, and continuous for all x larger or equal to n, the capital N, which is, well, the series itself, it starts with 2, so we wanted to show that it's true. Honestly, sometimes I'm not a fan of doing integral tests because it takes time, and I don't want to define a function and then solve that function, then the implication that, okay, the function converges, sorry, improper integral, it converges, therefore it converges well. But I think I can solve this by using let me think. I don't want to waste my time, but e to the power square of n is still true. It's larger. Yeah, it can't work. So Damn. All right. So let's try with integral tests. So integral tests. Now it's rare to use this test because usually most series can't integrate. It's tough to integrate some series. So what are the conditions? Okay, let us define a function. Let f of x is equal to 1 over, oh sorry, 1 over x, sorry, x ln x squared for all x larger or equal to 2. So it's a real number. X is it's a real number. Okay. So, but the behavior for the function and sequence are the same. So it should be no problem. And here, 1 infinity. Sorry, should be 2. 2. 1 is not defined. 2 infinity, so we have 1 over x ln x squared dx. Let u, yeah, I'm gonna solve, oh god, what's the name? It's not undetermined. It's not. It's, I forgot. But I'm gonna solve the integral without the bounds. Yep. I forgot the name. X ln x squared dx. It's not improper. Oh, sorry. Indefinite integral. We were solving an indefinite integral first. So here let u is equal to ln x. Now when you take the first derivative, it will be 1 over x dx. Then you can substitute your way here. And then here you have 1 over u plus c, which implies it will be negative 1 over ln x plus c. Nice. Oh, okay. So, all right. We have our in-depth integral now. We want to solve our definite integral. So we have, I'm going to start right here. 2 infinity 1 over x times ln x squared dx. Now by taking the limit b approaches to infinity to b 1 over x ln x squared dx, and then solve the improper integral. 1 over x ln x squared b2, sorry, that's not an answer, should be negative 1 over ln x. Limit b approaches to infinity for negative 1 over ln b plus 1 over ln 2. And you know this, as b approaches to infinity, ln b approaches to infinity, therefore the whole term approaches 0, therefore 1 over ln 2. This shows that the improper interval converges. Now, since it converges, therefore our series also have to converge. But the value of the series is not the same as our improper integral. But we know that both of them have the same behavior. Therefore, from here, 1 over n ln n squared converges. Okay. Well, put the absolute value, same thing, so it converges absolutely. Right? Very nice. Question 30. Okay. Now, question 31. Oops, sorry. 31, we have the series ln n over n ln n over n cubed. So here, one of the cool things about this one is you can use direct comparison test, but what is the proper p series to compare with? Now, one of the cool things about this series in particular for ln n over n cubed is that there's a fact where we have given this series, but n power c, where we want to choose the proper series that satisfy this to converging. Now, we know that this implies converges because p is not less than or equal to 1, then the series converges. So what is the appropriate p value? So here, 1 and 3. So 1 over n squared. I think that would be appropriate. And if it doesn't work, then try other things. And the more you try, the more you converge. Okay, so let's build the inequality first. Let's see whether or not it's true when we pick p is 2. And here ln n, and well, from here, we know this will always be larger for all n. Okay, now, all right. So if we build an inequality by direct comparison test, sorry, and both series have positive terms, so for all n, since converges, then this, wait, what button? Also converges. Okay, also converges. Now, even with the absolute sign you put in, it converges as well. So what does it imply to? It implies that it converges absolutely. So therefore, this series we have here converges absolutely. Very nice. Okay, is it correct? It should be. It should be correct. All right, 32. So far we did 7 questions. Let me drink some water. Bismillah. Mm, nice. Oh, that's, wow. Okay, so we have another series. All right. Oh man, this series is pretty interesting to see. We haven't stumbled upon root or ratio tests yet, but we will be. All right. N is equal to 2 to infinity. Now we have a very tough one here. Ln n over ln n. Okay. So, my instinct tells me that why not just integral test sub ln n, you will get u over ln u, but then the antiderivative will be, well, 1 over n, so does it work? Hmm, I suppose that, wait, no, sorry, I was thinking of something, but it doesn't work. Ln n over ln n, holy crap. Anthem test. I want to try anthem test. I mean, that's a simple test I could think of. This one, holy crap, it looks tough. Okay, anthem test. As long as it's not equal to 0, then it diverges entirely. So, let's see. By the L'Hopital's rule, no, yeah. It's in a indeterminate form. Okay, that's a good sign. So let me do it on my head, then I'll do the working. So 1 over n. I know it's wrong to do this. No, I mean, like, I'm not doing it yet because the proper way to do is define a function. If you want to apply the L'Hopital's rule, define a function, differentiate, and then claim that both of them have the same behavior, therefore you have the same limit value. I don't want to waste my time creating all the work because anthem test. The tough thing is if it's equal to 0, that it doesn't work. So yeah, not n 1 over. Right. Let me just do here. So, oops, sorry. Oh, log n, eh, n, log n. All right. Okay. It is. It diverges. All right. So Let's apply the nth term test. So here we know that if a limit of the nth term is not equal to 0, it implies that the series diverges. The series, not the sequence, the series. So let's let's apply to this. Limit n approaches to infinity ln n over ln n. Now this, as n approaches to infinity, our numerator approaches to infinity. Same goes for our denominator here. Okay, so apply L'Hopital's rule. I mean, observe. If you observe right, you see that ln n grows larger, I believe. Yeah, wait. No. I have to do L'Hopital's rule. All right. So let f of x is ln x over ln x for all x. Whoops. For all x larger or equal to 3. Now, yeah. So as the limit x approaches to infinity for ln x is an indeterminate form. Therefore, by applying if we differentiate, this cancels. Then we have. I'm trying to imagining it. Okay, ln x. So this is approach to infinity. So it's not equal to 0. So both of them have the same behavior. Therefore, our n term will also goes to infinity. Therefore, this series diverges. Okay, this series diverges. Oh man. Oh, the schema answer did a direct comparison test, but I don't care. I can't think of a proper direct comparison test because the way they did this is that e to the power of n. No. Who has the right mind to say e to the power of n will be the perfect comparison test? I will not be thinking of that, not at all. But yeah, anthem test works fine. Okay, all right. So number 33, we have another alternating series. So this usually goes it diverges or converge conditionally. That's the only possibility, honestly. So we have this. All right. So by placing the absolute value, okay, you will have this following series. Okay. And I would like to use direct comparison test. So I'll be comparing it with this. Whoops. That is an ugly sigma. Okay. 1 over n squared. So first we have to build the inequality. I want to see does it work. That's the beauty of series. You have to try and error because sometimes there are some questions where it's familiar. It converges. So I know it converges by DCT that you don't need to do the work. But sometimes, in my case, I can't do that. I have to do the work. So here you go. All right. So this is always be larger for all n larger equal to 1. So by direct comparison test, by DCT, we can build this following. We have to build the following. So n, I mean, in by observation, you could see that this will be larger than this. Then this whole term will be much more smaller than this term. Okay, but I'm doing algebraically so that everyone can see what I'm doing. So this is true for all n. Okay, now since this converges, then this series also converges. Now, the cool thing with the absolute value on our series is that if it converges, sorry, if it converges, then the entire thing converges absolutely. So that's very cool. So therefore, this alternating series, which is n over n squared, n times square n squared plus 1, converges absolutely. I thought someone's knocking my door. Hold up, give me a second to see. Okay, no one informed me early on. I was okay. I thought someone was knocking my door. All right. So yeah, it converges absolutely. So which question is this? Question 33. Yeah, absolutely. Okay. All right. This question 34. Okay, 34. We have this series, which is an alternating series where 3n squared over n cubed plus 1. So our constant multiple, I'm going to bring it out. Then we have this. Now I'll be focusing on this series only, and then I'll make a conclusion. All right. So by putting the absolute value, we know that negative 1 power of n can be cancelled. As so. Now we're gonna do the direct comparison test as usual. So I'll be taking these terms. I'll compare with this some series n squared over n cubed. So this will be n1 infinity 1 over n. So this diverges. We know it diverges because it's a harmonic series. Therefore, if we want to do, yeah, we can do it. So I believe when we build the inequality, I'm gonna build it on this right here. I always build the inequality just to see whether or not it's true for all n cubed plus 1, 0, 1. Huh. It doesn't work. Okay, it doesn't work for the comparison test, but it will work for limit comparison tests. Okay. Remember, if direct comparison test doesn't work, it doesn't imply that limit comparison test doesn't work. So, limit comparison test tells us that if the value of the limit is larger than 0, then if our known series diverge or converge, then our test series also diverge or converge. It depends on the series where we tested on. So, an over bn. An is our known series, bn is our test series. So, an will be 1 over n. And our test series will be n cubed over n cubed plus 1 over n squared. Right, if I'm not mistaken, an over bn, an is our known series, test series. Wait. Sorry. I sometimes get confused. An is our test series. Yeah, bn is our known series. Yeah, bn is our known series. Sorry. Because bn is our known series. Anyway, so test series n cubed over n squared over n cubed plus 1 n. So here, infinity n cubed over n cubed plus 1. Then we know that by dividing all terms with n cubed, we will have 1 over 1 plus 1 over n cubed, 1 over n cubed approaching to 0. Therefore, 1 over 1 plus 0 will be 1. Then this is larger than 0. Therefore, this series diverges. diverges. Now, how about our original series without the absolute value? So we have to do this. Obviously, alternating test series will be this suitable test. So n cubed plus 1. Okay. So, as usual, let un is equal to, new page, n squared over n cubed plus 1. So the first one will be un is always positive for all n larger equal to 1. Second one, we want to show that it is larger, it satisfies this condition. So un will be n squared over n cubed plus 1. Oh, this is tough because you have to show that this is true. So remember, besides the inequality, you could use differentiation. You differentiate and you could see that it's always be decreasing. Okay. The reason why I did the inequality because I want to show that it is decreasing. Okay, it decreases. So the other way is this. By defining a function, f of x is equal to x squared over n x cubed plus 1 for all x larger equal to 1. So now how do we solve it? By taking the derivative, you know the quotient rule. So here we have the following. Okay. And 2x minus x cubed. Okay. At x is equal to 1, it's still positive, the slope. But when x is equal to 2, it's a negative value, and so on. Because this is much more larger than this when x becomes equal to 2. So this implies that this is a decreasing function, which also implies for the n term to be decreasing. Okay, so is less than 0. Because the slope, when it decreases, the slope becomes a negative value. Then that implies that the function itself decreasing. So what does this mean? This means our n term will always be the un will always be larger or equal to the consecutive next term for all n larger or equal to 2. Last will be the limit n approaches to infinity for n squared over n cubed plus 1. We know this will always be larger faster than n squared as n approaches to infinity, therefore becomes 0. Okay. Now this converges by the alternating test series. -1 power of n. N cubed plus 1. Okay. Therefore, this series converge conditionally. Okay. Okay. Wow, this is a long one, 34. So let's go to, okay, 35 is a bit easier. Finally, we have an easier series. You know why? Even as a factorial, but you have to remember the two series that we've learned, which is root and ratio test. So Ratio test, what does it tell us? Ratio test. If P is equal to 1, the test fails. If P is larger than 1, it diverges. P less than 1 converges. Okay. So let's see. Over n plus 1 n factorial by replacing everything in. Oh no. Oh yeah. It works. I thought it was like, oh, it doesn't work. But yeah, it works. It works. Because this, since the denominator will grows larger faster than the numerator, therefore this whole thing goes to 0. This is less than 1. Therefore, this whole thing converges absolutely, which is very nice. Very nice indeed. Okay. Converges absolutely. Okay. All right. So let's go through question 36. We have, okay, another one. Another one. Another series where, okay, this, you could use Anton test, right? Anton test is the suitable way to solve this. You could say it alternates between some value so that it diverges. So the way we want to show is that given the series here, n1 infinity negative 1 power of n times n squared plus 1 divided by 2n squared plus n minus 1. Okay, now I'll be using Anton test because that's the best test of all, the most easiest one, and the most, not the less time consuming one of all tests that we've done. Okay, let me drink some water. So, and okay, so let's create a piecewise function for ourselves here. Okay, here we go. And the first one will be n squared plus 1 over 2n squared plus n minus 1. This is for when n is even. Then another one, n squared plus 1 over 2n squared plus n minus 1. This is when n is odd. Now, when you see, right, when you take the limit, n approaches to infinity, n squared plus 1, I'm going to take the term without the negative. This, both terms here, it will approach to 1 over 2. But this approaches to 1 over 2 as n approaches to infinity. This approaches to negative 1 over 2 as n approaches to infinity. So what does that mean? As n approaches to infinity, this term here will alternate. Will alternate between negative 1 over 2 and 1 over 2. Therefore, it diverges. Okay, so yep, it diverges by the Anton test. Okay, I want to try my current series. Let's see. I'll use series. I want something that's very nice. I mean, not too long. Hmm. I'll see. Because I have another file, but well, I have a few more questions I have to do. Okay. Question 37. We have a series. Okay, this you could use ratio test. Okay. So let us apply the ratio test. So ratio test, what does it say? Ratio test. as the limit n approaches to infinity, limit n approaches to infinity for where we have the first one. Um, well, -1 power of n, and then be -1 power of n, and then we have 3 power of n. All right, divided by n plus 1 n factorial. Okay, the way I obtain this is from exponent rules where we have this n plus 1, that we can separate them, and we know that we can separate the negative value as well. Okay, just a heads up. And n factorial divided by well, -1 power of n, 3 power of n. Okay, cancel. The absolute value cancels the negative, so that's nice. Now we have this limit n approaches to infinity, 3 over n plus 1 is 0, less than 1. Therefore, it converges absolutely. Okay, it converges absolutely. So, I think I have a few. Yeah, converge absolutely. Okay. So, how about question 38? Well, man, I have a lot of notifications. Give me. Okay. All right. That's someone. Okay. Okay. All right. So you have the question 38. We have this series now. 2 to the power of n, 3 to the power of n over n to the power of n. Well, we know, what is it? Root test. Very nice. So for this series, so limit n approaches to infinity, an square root of, no, the nth root. Sorry, the nth root. So this, immediately, the nth root will cancel all power of n's. So 6 over n is 0 less than 1. It converges absolutely from there. This converges absolutely. Right? It converges absolutely. So, okay, let's try another one. Well, we always try another one. We have question 39. Right, question 39. We have the following series, which is 1 divided by square root of n times n plus 1 n plus 2. And now I can use direct comparison test. I think we could use that. So I'll be gathering the n terms, the higher power of n. Yeah, you know what I mean. Like n squared n cubed. Yeah, the highest power will be n cubed denominator. The square root of n cubed. So that will be the series that I'll be comparing. So here we have the series that we're comparing, 1 over n cubed. Well, it will be n, 3 over 2. So I know this is a p series. It's a p series. Now, this p series tells me that 3 over 2 is larger than 1, so it converges. Okay, it converges. So let us try, and by using the direct comparison test, see whether we can build an inequality and we can solve from there. So n times n plus 1, n plus 2, then here will be 1 over n to the power of 3 over 2. Okay, so I mean multiply both sides, then square both sides at the same time. So n cubed is equal to n plus 1, n plus 2. And obviously, this is always larger or equal to. Okay? Because this term will be larger. It will have it has a constant, it has another addition. All of them are positive, and they are adding to one another, which makes it much more larger than n cubed, as it if we have only n cubed as it is. Okay. Wow. Yeah. Okay. So what are we about to do, gentlemen? So we're gonna build the inequality for the direct comparison test. So this is it. One right, yeah. Um, Therefore, the series here converges. And I can argue that it converges absolutely because with the absolute, it still converges, so this converges absolutely. Very nice. Okay, very nice. Question 40. Yeah. Question 40 we have here. Again, another series where we can use direct comparison tests if we can. So n is equal to 2, infinity, 1 over n square root of n squared minus 1. So by DCT, I know there's a series where it is suitable, which is 1 over n squared. Okay? Because with the square root, n squared. Now by building this, n squared minus 1, that we have n squared, then it should be a-okay. N squared minus 1, that we have 1, 0. Oh no, it doesn't work. It doesn't work. Because if it converges, then the right hand side should be larger, right? But in this case, it doesn't work. Surprisingly. So, limit comparison test will be the trick. Okay, let's try again. This is the downfall. No, this is not my downfall yet. Okay, let's try again. Limit comparison test, but we will be using the same series. Now this converges. Now limit comparison test, what does it tells us? It tells us that A and B and A and our known test series, B and our known series. So limit n approaches to infinity, where n is 1 over n square root of n squared minus 1, and then here will be n squared. Right? And then, well, this tells me that n over n squared minus 1. And this, I could factor n squared, so it will be n squared 1 over n squared. And we know that the square of n squared will be n, so this can cancel. You are left with 1. Remember, this is a positive domain, so it should be no problem. By bringing out the square of n squared, there will be no absolute value because we don't need it, because n is always positive, so does it affect anything, even with the square root, the square n squared, n squared. Yeah, sometimes we have to mention what these things, because people will think like, oh, well, yeah, square of n squared is n. No, we have to consider that it can be a positive value. Okay, n can be positive or negative, but in this case, our domain is always positive for n, so it should no problem. Okay. Now, 1 is larger than 0, so what does it mean? It means that since our known series converges, our test series have to converge as well. So, 1 over n square root of n squared minus 1 converges. We are currently 1 hour in. Okay, so far we did a lot of questions. Did 15. Wow. Okay. 15. Okay. So, oh yeah, it converges absolutely. Even with the absolute sign, it still converges, so it implies it converges absolutely. Okay. Okay, 41. Alright. We have, okay, I have four more questions for normal series, and then power series. I have nine for power series. Okay. I mean, no problem. Can do that. Then Maclaurin series and then Taylor series. Okay. Alright. I'm gonna pause for a few minutes, then I'll continue on after okay. That was a nice break. So question 41. Now question 41, I'll be okay. Question 41. Hi Mila, sorry. Okay, well, I can just. Alright, 41 will be 1 minus 1 over square root of 3 square. Then plus 1 over square root of 3 power 4 minus 1 over square root of 3 power 6. Then plus 1 over square root of 3 to the power of 8. And then blah 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 blah. Now, obviously from this, the sign positive and negative sign, it alternates. Now, I would like to express this as a series because they want me to know whether it converge or diverge. Then okay. So this is our first term. So for our first term to be 1, it has to be power of 0, right? So n to n, negative 1 power of n. So wait, it's not power of n, is it? Negative 1. Yeah, yeah. So n our first term is, well, the 0th term. I'm gonna make it as n0. So we will have 1, and when n is 1, it will be this following. So it matches with the sequence here, and it matches. Right, a good sign. So now we'll be expressing it as a sum. So here is equivalent to this. Okay. All right. Now, hmm. Well, we should root test. Sorry. By using root test, you will. Oh, it's not B. It's N. You can determine whether it converges absolutely or diverge. But remember, this root ratio test, if it diverges, it doesn't diverge for the original series. It diverges for the absolute, because we put the absolute beforehand. So that's something to take note of. So here, limit n approaches to infinity, we have negative 1 power of n. Sorry, I have to put the absolute first. Okay, and then the negative value will be cancelled out. Sorry, I forgot to put here. All right. So here will be, well, 1 over 3. 1 over 3. Less than 1. Okay, so this implies it converges. Therefore, converge absolutely, because we have the absolute value in it. Okay, so hopefully I'm correct with that, and yeah, converge absolutely. Very nice. So question 42. Oops. Question 42, we have the series. Okay, negative 1 power of n over with e to the negative n plus 1. Okay, so as usual, I'm going to put the absolute value sign. Now we are left with 1 over e to the power negative n plus 1. And then we can express this as this other form, e to the power of n over e to the power of n plus 1. Okay. Or, I mean, sorry, I just remembered. When you take the limit for this one, we could use n-term test. Okay, I'll define it first. Negative 1 power of n. I define it as a piecewise function here. So it will be negative 1 over e to the power negative n plus 1. And then 1 over e to the power negative n plus 1. This is for when n is odd, n is even. So when we take the limit, 1 over e to the power negative n plus 1, this is equivalent to e to the power of n over e to the power of n plus 1, which we know this is 1. Now, based on our piecewise function, as n approaches infinity, this term, sorry, alternates between negative 1 and 1. Therefore, by end term test, this series diverges. Sorry, it's not 1, it's 0. Diverges. It diverges. So, what else? Well, we have question 43. Oops, zoom in. 43, we have a series where it starts from 0 up until infinity. And then, we have this. 1 plus r squared plus dot plus r power of n, where r is between negative 1 and 1. So, remember, in this case, right, this is basically a series. And by obtaining that series, we know what? It's a geometric series. And a geometric series, we can express it as a function. Now, what is it? What is the function will be? So, if I'm not mistaken, it will be, wait, let me do it separately so that I could see it. Sorry. So, 1 plus r squared plus dot plus rn. And then we have here is the sum where this is it. And we can do it as a function, which is 1 over minus r. This is when negative 1 r 1. Okay. Now, it's basically in a way that I could think, right? This, if not mistaken, oh no, Rn. Oh, we have n. I mean, okay. Wait. Rn and r. Oh, series anyway. Okay. And now, we can express this as the following. Okay. So what does this implies to? I mean, when you take the limit, right? When you take the limit, n-term test, this doesn't equal to 0 because our r, I believe, Yeah, our r will not be 0 because r is not 1. If it's 1, that is 0 lah. But in this case, the inequality shows that 1 and negative 1 does include, therefore doesn't make it 0, therefore it diverges. This series diverges. Okay, as long as it satisfies the inequality, then it diverges. Right. So yeah, anthem test. By the way, the limit is an anthem test. Okay, 44. All right, 44 is nice. I think. I think so. Because we can do, I believe, where n plus 100. Oh, okay. We are given an alternating series. And then we have the square root of n plus 100 minus square root of n. So I'll be taking the absolute value. And then we are left with this following. Now taking the conjugate, we can express it as n plus 100 plus square of n. And remember, this, by using anthem test, oh yeah, you can use anthem test. Oh yeah, okay. Alright, I think using anthem test, yeah. So by using anthem test, we can get the following. Oops. Let me express it as this. Now, first, we define it as a piecewise function. Oops. This is for when n is odd, n is even. Now, this top part, when n approaches to infinity, it becomes negative infinity. But when the bottom part, when n approaches to infinity, it becomes to positive infinity. So the way we argue is that n approaches to infinity, this whole term will alternate as well. Will alternate. Alternates between negative infinity and infinity. Therefore, it diverges. I don't want, we know anthem test, okay? This is anthem test, so it diverges with the anthem test. Right? All right. So let's go to a new section, which is power series. Is there any other questions where it's going to be series? Holy crap. When I saw the advanced question, I was like, wow. Wow, okay. Ooh, there's another one. Okay. There are more questions where I want to do, but I'm just going to do the ones where it is obvious. Right. Okay. All right, let's go through with power series. Okay. So power series, this is a new section. Oops, sorry. Power series. Now, power series, remember the general form for power series is this. Okay, where this is a coefficient and it's a sum of polynomials, basically. So now we want to know the interval of convergence, absolute convergence, and some x value where it converge conditionally. Okay, so that's the idea we want to do. So we have the series n shape of n, and we want to know what interval it converges absolutely, conditionally, or even if there's an x value where it converges conditionally. Okay, so here we'll be using with tests. So the limit n approaches to infinity for an, that's the value of it, square of n, no, n root, sorry, now here, sorry, we could, yeah, that's the value, n plus 4, sorry, x plus 4, power of n, over with n, 3 power of n, 1 over n. Limit n approaches to infinity, we know that this is x plus 4, the bottom will be n power of 1 over n, 3. So basically 3 times 3 and 1 over. So when you take the limit, remember one of the theorems that we did before about sequences, this approaches to 1. Okay, it approaches to the value of 1 if I'm not mistaken. So we will have 1 and then the whole thing will be 1 over 3. So divided by 1 over 3. Now to determine whether it converges, remember root and ratio test tells us that if the value is less than 1, it converges absolutely. So here we will do the following, less than 1. Now this implies that we could open it, that we can find our interval of absolute convergence like so. Okay. Now we want to know whether the endpoints -7 or -1, does it converge conditionally or diverges entirely? So x is equal to -7. Now when x is equal to -7, our series will be, so yeah, -3 power of n over n 3 power of n. And when we simplify it further, we are left with an alternating harmonic series. Now we know that an alternating harmonic series converge conditionally. Yeah, converge. Here we don't need to show because I assume all of you know how and why it converge conditionally. If you want to know why it converge condition, you could check out. You could try by putting absolute value. When you put absolute value, it diverges, but when you apply the alternative series for the original series, it converges. Therefore, it converges conditionally. But here we know that the alternating harmonic series converge conditionally. Say. Okay, so x is equal to, okay, the next one is x is equal to -1. So when x is equal to -1, our series will be the following. 3 power of n over n 3 power of n. So this implies that we have 1 over n. And this diverges, obviously diverge. Now, for interval, okay, interval of converge, absolute converge, sorry, interval of absolute convergence. Interval, I'm going to use a short form this time, interval of convergence absolutely. So IOCA, interval of convergence absolutely. So that will be -7. I'm on the interval form, -7, -1. Now, interval of convergence. Okay, interval of convergence, it includes the when x converge conditionally. So -7 including here, it includes -7. And now x -7, the series converge conditionally. Okay. So that is for question 45. Oh, and the radius 3. Yeah. Forgot to mention, this is our radius right here. Let me make it red pen here. This is our radius. Okay. All right, question 46. Question 46, we have. This is a tough one. We have another one. So, n is equal to, n is equal to 1 to infinity, and then x minus 1 power 2n minus 2 over 2n minus 1 factorial. Oh man. Hmm. Sorry. So, for this one, we have to use ratio test. Ratio test. And by taking the limit for this, then we can find the interval convergence. So, here, the first one, when we replace n plus 1, it will be x minus 1 to the power of 2n times with x minus 1. Okay. Wait, 2n plus 2 minus 2. 0. Oh, 2. Again, like that. And then divided by 2n plus 1 factorial. Okay. Yeah, the bottom part I can like express like this. Oh wait, 2n plus 1, right? Yeah, yeah. Okay, and then this one will be 2n minus 1 factorial divided by x minus 1 to the power 2n, x minus 1 to the power 2, negative 2, sorry. Then this power negative 2, I can bring it up, it becomes x minus 1 to the power 2. Cancel, 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 cancel. Right, so we are left with the absolute value of x minus 1 to the power of 2, and the limit, n approaches to infinity, we have 1 divided by 2n plus 1, 2n. So this approaches 0. So this entire thing approaching 0 less than 1. So what does this mean? For all x inside here converges. Absolutely. Nice. So any x, it converges absolutely, if not mistaken. Yeah, it converges for all of them. All of them. Okay. 2n minus 2 minus last series. Current. I think that's about it. I'm not going to show much. 25 to 46, which means that I've already showed around 21 questions, a combination for everything. I'll try to make another part, maybe tomorrow, maybe in the future, because the test is on this Wednesday, and I haven't teach Maclaurin series, Taylor series. Okay, and then the estimation error. I mean, those chapters are tough, man. But yeah. So yeah, any questions, just ask me in the comments, and I'll try to answer as much as I can. So yeah, thank you very much, and I'll see you later. Bye bye.